All right, we're going to take a look at some three-dimensional shapes now. As opposed to finding areas between curves in a plane, we're going to find some volumes, and we've had a little bit of experience with dealing with volumes so far. And you remember what it boiled down to with previous work with volumes is that we had, when we made a rectangle, okay, instead of summing up all the rectangle, when we revolved it around an axis or some horizontal or vertical line, it became, instead of a rectangle, became a three-dimensional cylinder. Okay? And so instead of summing up the areas of rectangles, we summed up the volumes of cylinders, and that gave us a total volume, etc. Now we're going to do this idea of revolving a rectangle around an axis or a line of any sort is going to be, we're going to deal with that essentially tomorrow. What we're going to look at today is what we call volumes of cross sections of solids. And so we're going to start with an example here, and I'm just going to use the y equals x squared function. And we'll say on 0 to 9. And what it boils down to is we're going to be given a function like y equals x, radical x, I should say. Could be really any function. And we're going to have some boundaries just like we had with the areas. Okay? If we want to find the area under this curve, we would just simply write y equals, or our area would be this integral from 0 to 9 of radical x dx, and that would give us the area. Now, what it boils down to, though, is that this is going to be essentially what my base is, okay? And what I'm going to do is that I'm going to take slices that are perpendicular to the x-axis, like that, for instance, okay? And this is going to create a solid, okay? Where the solid, and this is where it's going to be difficult to visualize because we can't draw in 3 dimensions on two-dimensional paper. Okay, what it boils down to is the slices that we have, they're going to be perpendicular to the x-axis, and that's going to be something that's given. They're going to tell us that it is perpendicular to the x-axis. Okay? And that each slice is going to essentially come out of the paper at us, if you will, okay, as some kind of shape. Okay? So one shape might be, say, a rectangle, or let's say a square. We'll do, I guess, the easiest one first. So ultimately, I'm going to try to draw it in 3 dimensions as it's essentially coming out of the paper at us. Okay? So something like that. So that particular slice, it's going to come out of the paper at us as a square. So that shape is going to be a square. Okay? So if you can picture it, again, it's difficult to draw 3 dimensions on a 2-dimensional paper, but ultimately each slice is going to be going to come out of the paper at us, okay, and it's going to make a square. So think about what that's going to look like. If I had my square right there, if I had drew a square right here, that square is going to have a different length than this square. True? And therefore, would it come out of the paper as much at us as the other one did? No. In fact, it's going to start here at 0. It's going to be a square that's got no area whatsoever. True? And it's going to keep getting bigger. So once we get to this point 9 here, where x is 9, okay, then the squares are going to be fairly tall. True? Because it's going to come out. If that is 9, 3, if you will, okay, the dimension of that square is 3. It's going to come out of the paper at us 3 units as well. Okay, whereas if I pick this point, let's just say for argument's sake that this is 4, and remember we know that that point then would be 4, 2. If it's 2 in that direction, then coming out of the paper at us, it's 2 also. Okay? So as we move to the right, the squares are going to be taller, if you will, as they come out from the paper at us.
It's kind of like slicing bread.
Kind of like. Yeah, if you can think of it like that, because ultimately, again, as we go to the right, though, these squares are going to get bigger. I mean, bread pretty much stays the same height all throughout. The bread would have to kind of be curved down, if you will. Okay. Because every x that we move to the right, the square is going to be a little bit bigger. Okay. Because this dimension is going to be bigger. Therefore, coming out of the paper at us is going to be a little bigger also. Okay. Now. Question is, how do we account for that situation then if we want to find the volume of such a solid, okay, that would look like that would be made up from these squares? Okay. Well, the key issue is making sure that we can write an equation for the area of one square. So in our particular problem, okay, if we were to pick a particular x, let's say I made that 4 a minute ago, but ultimately it would be x if I just pick some random spot in the interval. True? And so ultimately, what would this dimension be right here then? If I picked an x instead of 4, 2, it would be x radical x then, wouldn't it? Wouldn't the y-coordinate be radical x? We plug in x. So that height right there, the height of that rectangle that I have drawn there, the square that I have drawn here is radical x. Now, if that's radical x, if you will, then what are the other three dimensions? The radical x, this thing's a square, true? So, and again, start out with a general formula. We know that the area of a square is s squared. True? Okay. So therefore, what is our area then of our square? It's radical x squared, because what is our length of side in this thing? It's radical x. Okay. Alright, and so therefore our area is x. Okay. And once we establish that, we use our geometry formula for whatever shape that our slice is. Okay. Then we have our geometry formula. We plug in whatever our dimension is. In this case, there's only one dimension because it's a square. Okay. And we get a formula now for the area of that square. Now, what would be the thickness of that square? Ultimately, if we want to find the area of all the squares together, we want the thickness to become infinitely thin, don't we? Okay. And therefore, it's going to become an integral, and we'll go from 0 to 9 of x dx. And in general, like I said, it's going to come from s squared. Okay, why is there no squared here? Because we already simplified the integrand. We could have wrote in here radical x squared, because our side length of any given square is radical x. So we could have wrote radical x squared, but really that's just x. True? So if we calculate, okay, and again the thickness being dx, because it's infinitely thin, then we can figure out what our answer is here. If we do our x squared over 2, we're going to get 81 halves. And that right there is going to be the volume of a solid that's generated by making squares out of this region. But again, key issue is that we start with our formula for what shape is the slice. The slice is a square. So we start with our area equals s squared formula, and we plug in what is the side length of a general square. Okay? This being the general square, we're good to go. Now, we're going to use that same region, and we're going to change it up a little bit. This time, our slice that we do, our horizontal or vertical slice, okay, this time instead of a square, okay, it's going to come out of the paper at us as a semicircle. Okay. So if you can visualize that, okay, now instead of being a square shape, which would have kind of like cornered edges on the top of our shape here as we go from left to right, this one's going to be fairly smooth as we go from left to right because it's going to be semicircled all the way through it. Okay. Now again, this is the difficult part about visualizing because it's hard to draw 3 dimensions on a 2-dimensional paper. Okay. Now before we answer the question though, I want you to take a look at in your book here on page 391. In your homework assignment, they have some better pictures because they have better technology than my crappy art, so they can draw pictures a little bit better. So they have an ellipse that's in or a circle that's in the coordinate plane, and the cross sections here are circles. So you notice that number 1 picture that kind of looks like what ours would look like, except for instead of circles, we're using just half circles. So we're not going into the page; we're just coming out of the page, if you will. Okay. We could adjust this and we could do full circles too, which we may in a minute, but ultimately, in our particular case, we're just interested in the volume that's going to be generated by making half circles out of these slices. Now, again, like we did a minute ago, we need to figure out what is going to be the area of a half circle in general. That's what we need to start with every time. So it'll be a half times pi r squared. True? Now, the question is, what is r for this circle? Well, that distance right there would be r then, wouldn't it? Or we could think of it as the bottom part of it also. Okay? And let's think about what would the diameter here of this circle is going to be the radical x again, isn't it? Okay? So ultimately, what would r be? It'd be radical x over 2. So wouldn't that be an expression right there for the area of a half circle in my picture? True. And ultimately, the integral doesn't change. We're still summing these up from 0 to 9. And so ultimately we could put a half pi out in front. Matter of fact, we could put a 1/8 pi out front, because if I square that, I'm going to get a 2. I'm going to get 2 squared, which is 4. If I take a quarter out of there, I got a quarter and a half out of there. It makes an 1/8. And then ultimately I'd have x dx again then, wouldn't I? Because I'm squaring that radical x part. And so in turn, we're going to wind up with 81 pi over 16 is our answer. Remember, remember the 0 to 9 of x dx was just this. Right? If I multiply by an eighth pi, 1/8 times this is going to be 81/16. Now, just for argument's sake, would you expect that that this one is going to be more volume, or this one? More volume on the squares or the half circles? Squares would seem more, so let's check it out and see if that's a fact. So 81 over 2, we got 40 and a half. 81 pi divided by 16. Quite a bit less than, isn't it? All right. Questions on that one? All right. So that's kind of the gist of it. We're going to do another couple here just for argument's sake, just so we can see a couple other shapes. How would that have changed, just for argument's sake, if we had said that that slice was a full circle? So not only came out of the paper, but it went into the paper.
Our area won't be
Ultimately, remember when we did this, our original area was a half pi r squared, right? So wouldn't this half just not be there? Okay. And so with that said, that would change our answer completely, wouldn't it? Okay. So when we got to this point, the half wouldn't have been there. We would have just had a quarter out in front because of the x over 2 squared, radical x over 2 squared. So we had a quarter out in front. So ultimately, wouldn't it be 81 pi over 8? Essentially be double of what we got for the other way, wouldn't it? All right. So with that said, what if we did same region, same slice, and we said that that we had an isosceles triangle instead? So every slice that we draw is going to come out at us as an isosceles triangle. The base is going to be in the plane. The isosceles part is going to be like that, we'll say. Fair enough? So our question then is, can we write an expression for the area of that triangle in terms of x? True? So same problem that we had, it's just a different shape, so we're going to start out with a new formula. Alright, so let's see if we can do it. So we got b here. Wouldn't b just be radical x? Considering that to be my base. Okay. Now what about the height? Somehow we need to write that height in terms of x. Well, I'm going to take this slice right here. I'm going to draw it in 2 dimensions. So if this were my slice, and my base was radical x, keep in mind. Question is there a way to write an expression for h here, the height? Keeping in mind that when I have an isosceles triangle, we drop that line down for h. Okay, it does a number of things. At number one, it bisects the bottom, if you will. Okay. It makes a right angle here. It also bisects the angles at top. Okay. We know these two angles are equal because it's isosceles. Okay. So some of our information that we know from geometry. And like I said, the question is, can we come up with an expression here for the height? Okay. And if so, what would it be? Well, we know that those would both be radical x over 2. These two expressions, right?
tangent of 45 equals x over.
Well, one of the issues, though, that we got is that if I had an isosceles triangle, it could very well look like that, couldn't it? And so with the angles here, are they going to be the same as the angles here? They're not, are they? Okay. So bottom line is, if I wrote some tangent sentence here, which I could certainly write a tangent sentence, I'd need to know something about the angles here, though, wouldn't I? Like I said, because that triangle right there and that triangle right there, they wouldn't be the same at all, would they? Even though they had the same radical x over 2 for that side right there, that height here would be completely different depending on the angles, wouldn't it? Okay. So bottom line is, can we write an expression for h in terms of x then with this information? We'd need to know an angle, wouldn't we? Okay. So the answer is no, we can't. So let's change the problem a little bit and make it something that we could do. Let's just say, for argument's sake, that it was that was not only isosceles, but it was equilateral. If it were equilateral, then remember these angles would all be 60s. This would be a 60 then, and when I cut it, that'd be a 30. So now I have a 30, 60, 90 right triangle. Okay. With this being the short side here, across from the 30, okay, then the height here, the relationship in a 30, 60, 90 triangle is always x, x radical 3, 2x. Hypotenuse is always double. Short side, the long side, the 60-degree leg is always going to be x radical 3. And so that means that my height here in this problem then would be radical 3x over 2. Okay. It's going to be whatever my short side is times radical 3. And if I do radical x over 2 times radical 3, that's radical 3x over 2. So there's my height. So if I knew that was equilateral, then I could find the height. Or if I knew something about the angles, then I could do it too, but then it'd be kind of a pain in the neck really, because I'd have sine or cosine or tangent in there as part of my integrand. So we may or may not be able to solve it if we did, even if we did know that. Alright, so that right there would be an expression for the area of our triangle, which I changed to an equilateral triangle. Alright, so if I have a 30, 60, 90 triangle, and the short side right here is radical x over 2. Okay? The long side, which is our height, is always going to be the short side times radical 3. Because this is our model that we're using for 30, 60, 90 triangles. If I know the short side is x, to get the long side, I multiply by radical 3. So therefore, my short side, which I know is radical x over 2, times radical 3, is radical 3x over 2. So, with that, again, I have an expression now for the area of one triangle. True? So how do I sum up the volumes of all the triangles? I write a what? I write an integral. And if I do the math on this, I'm going to end up with x radical 3 over 4, I guess, dx. You take the 1/4 out if you want to, but either way, once we get the expression written, okay. So these two together, remember, are 3x squared. X squared can come out as x. 3 stays in. 2 times 2 is 4. So that would be our integrand. And in this section, unless it says do it analytically, then it becomes calculator problem from there. Okay. We ultimately know that that's a constant here, so we could do, it's pretty easy to do by hand because your antiderivative would be x squared over 2. Right? Factor the 3 radical 3 over 4 out. X squared over 2. Put a 9 and a 0 in there. Right? Pretty much home free. Alright, so ultimately the problems that we're going to work here in this section are going to be very similar to that. We're going to be given some region that's in the xy plane, and that's going to be the base, okay? And then whatever the cross sections are like, okay, we're going to draw a slice. We're going to draw the cross sections as stated, whatever they may be circles or half circles or squares or rectangles, etc. Okay? And ultimately our key issue here is to start with a geometric formula for that shape, whatever shape they tell you the slice needs to be, right? And then try to fill in the blanks with expressions in x. And once we do that, then we can sum up all those shapes by writing an integral from whatever to whatever, in this case 0 to 9, of our area formula, dx, and that ultimately sums up, okay, the areas of all these infinitely thin slices of triangles, which ultimately creates a volume. Alright, I want to look at one more here. Let's go page 391 here, look at number 10. Here's your picture. They give us, just to look at another example here, because like I said, most of the problems are going to be really exactly the same as what I just did here for any of these. They're just a different base and whatnot. But ultimately here we have a base of a solid that is the disk x squared plus y squared less than or equal to 1. Cross sections by planes perpendicular to the y-axis this time, notice. And if you look at the way they have this drawn in 3 dimensions, here's our y-axis, here's our x-axis. So this time we have horizontal slices. True? And it says that these are isosceles right triangles with the leg in the disk. Okay, one leg is in the disk. And if these are isosceles right triangles, remember if that and that are equal, what does that make these angles? Makes them both 45. Isosceles right triangles are always going to be 45, 45, 90. So to do that one, I'll let you to kind of work on figuring out what the formula is going to look like. It's very similar to the one we did here. But remember when I have a 45, 45, 90 triangle, the relationships are going to be if that leg is x, then what's this leg? this thing is x. And if you forget, you can do the Pythagorean theorem with those two equal x squared plus x squared equals c squared and figure out c, but it's ultimately x radical 2. So those are the relationships between the side lengths when we have a 45, 45, 90 triangle. So you'll need to use that information to figure out the height possibly. Okay. And ultimately, again, though, the key issue is can we write an expression? Okay. And you notice again, these are horizontal, so we're going to write an expression not in x, but in y. Still going to go from -1 to 1 because it's a circle with a radius of 1, so we're going up and down instead of left and right, but either way we're going from -1 to 1. Okay? So that would be one where we're going to write an expression in terms of y instead of in terms of x. So with that equation that you have there, x squared plus y squared equals 1, okay, then you'll have to manipulate that equation and have it written x in terms of y instead of y in terms of x. Okay? All right, so we're just working on the first 10 on the assignment for today, for tomorrow. So just 1 through 10 only. So let's see if you can set these up as I did and hopefully come up with the right answers. So we'll work on those for tomorrow and we'll do questions at the beginning tomorrow.